Hey everyone, let's get started. First of all, thank you for coming to today's webinar. I'll be going over what's new in STAR-CCM Plus 2406. I'm Matt Chan, CFD Application Engineer at SDA Software. My background is mainly on external aerodynamics. If you have any questions, you can ask at the end of the presentation or just type in the chat. I'll try to answer all the questions at the end of the presentation. Without further ado, let's start looking at today's agenda. This is today's agenda. I'll start with the company background, then I'll dive straight into the new features in the version 2406. Today, I won't be able to go over all the new features in this new version, so I only highlight the top new features. But towards the end of the webinar, I'll cover ways that you guys can explore the new features on your own. I separated the new features into two big categories, modeling capabilities and solution acceleration. There are 6 top new features in the modeling capability categories. 4 of them are related to multi-phase flow. The other 2 focus on battery design and heat transfer. Besides those 6 features, there are 3 more new features that can help reduce solution time and improve computational efficiency. So I put those 3 features in their own category, the solution acceleration. Lastly, like I mentioned before, I would like to share ways that you guys can explore the new features on your own. So I'll put it at the last towards the end of the presentation. Let's start with the company background. Before covering the new features, I would like to give you guys a brief introduction of our company background. We are SDA Software, which is a sister company of SDA. SDA is a structural design and analysis consulting firm. We provide expert simulation and design consulting services to the aerospace industry. SDA Software itself is a Siemens value-added PLM software reseller. We provide sales of CAE and CAD tools. All the softwares are listed on the right-hand side. We also provide training for female with NX Nastran on introductory and advanced levels. We also provide training for FiberSim as well. Let's talk about the first category, modeling capability. In this new version, STAR is further expanding their multi-phase modeling capabilities. New models are added to offer a more robust and efficient alternative for multi-phase application that were previously a little bit too expensive or too complex to model. The very first feature I want to touch base is the mixture multi-phase MMP to Lagrangian multi-phase LMP phase interaction. Previously, hybrid multi-phase applications with a free surface are usually modeled using the volume of method, the VOF method. The VOF method is generally a little bit more expensive for resolving the free surfaces compared to using the mixture multi-phase with a large-scale interface approach, short for an MMP-LSI approach. The MMP-LSI approach is a cheaper alternative for resolving the free surfaces, but the MMP to LMP phase interaction was kind of lacking in the previous version. But now with the latest version, 3 new MMP to LMP phase interaction models are now available. They are the LMP impingement model, the resolve transition model, and the subgrid transition model. Let's briefly talk about the functionality of these 3 models. The LMP impingement model was already previously available, but it was only for the VOF method. But now the LMP impingement can also interact with the MMP LSI free surfaces. Let's take a quick look at the LMP impingement demo in the bottom right corner. We can see that the LMP particle is immersed into the bulk fluid when the LMP particle impinges the free surface, considering the droplet and the bulk fluids are the same fluid. Then we look at the transition of the resolve transition model. That model specifically enables the transition from MMP blobs to LMP particles when a certain diameter or other criterion is met. And then on the other hand, we have the subgrid transition model, which does the opposite of that. That specific model allows the transition from LMP particles to disperse MMP when the particle diameter or the Stokes number is small enough. And with these new models, the MMP-LSI approach can essentially replace the VOF method in the hybrid multi-phase simulations and help reduce the associated computational expense that was associated with the VOF method before. And as you can see in the bottom left corner, I have something called a more info path. That is there to help you guys to find more information in the STAR-CCM documentation in case you guys are interested in learning more about this feature. And towards the end of the presentation, I'll go over how to use this more info path to navigate through the STAR-CCM documentation. So a demo of the oil jet and crossflow configuration is shown on the top right corner. To better understand how these models play a critical role in improving the computational efficiency, we're going to take a closer look on the demo to see how these models are implemented in the first place. So in the oil jet demo, the initial jet breakup is actually resolved using the MMP-LSI model that provides a sharp reconstruction of the free surface. And then due to the nature of this flow, the laminar jet will eventually transition into the turbulent jet along the oil entrainment into the primary flow, and that forms like large vertical structures like large blobs. And at a small enough diameter of these large blobs, it is actually more efficient to model these large blobs as LMP particles instead of resolving the tiny small free surfaces for these larger blobs, because that requires a lot more mesh refinement around those free surfaces. So this is where the resolved transition model becomes very handy, because you can apply the resolved transition model and set a certain specified diameter. And then as long as the diameter is detected by the model, then it'll basically transform the MMP blobs into LMP particles. To even add more another layer of realism to this demo, the LMP primary and secondary breakup mechanisms are actually introduced. With the breakup mechanisms, the LMP particles will further break up into smaller droplets and populate the primary flow downstream. But when the numbers of these tiny particles grow drastically, the particle tracking for these particles becomes very heavy for the solver. And since these tiny particles are really large in quantities, but small in volume, it is actually suitable to model these tiny particles as dispersed MMP due to the fact that they're pretty low in volume fraction. And the transition, like I mentioned before, can be handled by the subgrid transition model to transform the tiny LMP particles back to the dispersed MMP. Hopefully this demo highlights how you guys can now replace the VOF method with the MMP-LSI approach using the new models for hybrid multi-phase applications and with a more computational efficient approach. Besides the MMP to LMP phase interaction capabilities, the LMP to LMP phase interaction is actually introduced for the first time in STAR as well. The new LMP to LMP phase interaction is offering a realistic approach to model water management applications like a windshield wiper. So free stream phase now can interact with wall-bound phase with using the new LMP to LMP phase interaction, and the transfer from free stream phase to wall-bound phase is now possible, and you can do a deposition model. So a demo of the windshield wiper is shown on the right-hand side. This specific demo is simulating deposition of rain droplets on windshield. We can see that the rain droplets are modeled with free stream phase in blue when they're airborne, and the droplets is transferred into a wall-bound phase in red at contact with the windshield. To make this demo a little bit more realistic, the phase interaction is even further filtered by a particle diameter. So the transfer model is only applied to the smaller droplets, and splash mode is applied to the larger droplets to further break up the large droplets into the smaller droplets. So the broken up droplets will eventually meet the particle diameter to activate a transfer model. Before this update, to simulate this sort of applications, user would either need to use the expensive VOF method to resolve all the free surfaces of the droplets, or adopt a fluid film solution with less accuracy. So this new LMP to LMP phase interaction essentially enables realistic water management simulation now with lower computational costs and retaining the high accuracy. And more information on this deposition model can be found in the more info tab as well. Let's talk a little bit about the new things to the smooth particle hydrodynamics. So also known as SPH. The SPH module was introduced for the first time in the last version, 2402. And this version, STAR is continuing to improve on the capability of the SPH module. A new inlet boundary condition is added to the SPH module in this version. The new boundary condition enables injection-based multi-phase simulation like powertrain lubrication and spraying. User can now assign a velocity or a mass flow inlet to boundaries to account the effect for an injector, for say. And rotating and static inlets are also available, so that like applications like e-motor cooling are achievable with the SPH workflow. The SPH workflow is generally a little bit more advantageous because it has the shorter turnaround time for a highly dynamic free surface applications. Since it is independent of volume mesh, that helps avoid having fine mesh refinements around those highly dynamic free surfaces. And on the right hand side, what you just saw is a demo of an injection-based powertrain lubrication. You can find that there's a similar tutorial in the more info path in the bottom right corner. And then you can start learning how to set up the inlet conditions. Moving on to solid particles. So a new particle agglomeration model is replacing the legacy parallel bond model and the discrete element method, also known as STAR-CCM. This new model basically provides more flexibility for granular applications, which involves particle agglomeration and deposition. In the legacy model, the solid particles have quite limited options in the bond formation and bond stiffness. The comparison between the bond formation and bond stiffness options are shown in the bottom left table. We can see that the particle agglomeration offers the new user-defined options for both bond formation and bond stiffness. This is critical because this allows user to fully customize the new model for their own applications. Let's take a quick look at the demo on the right-hand side to understand how the new model can be customized for a granular flow in a wet granulator. So user can now assign a conical region around the center of the wet granulator at a given time, and then activate the particle agglomeration model. And then particle will start bonding within that region. And then after like a certain time, you can actually cut off the conical region and then turn off the bond formation. And then you can just basically observe the mixing behavior between the bonded particles and the individual particles. And also to be noted that this new model actually also bonds with boundary as well. So now DEM particles, excuse me, actually is able to bond with like walls or airfoil surfaces. So this actually enables applications like aircraft icing or sand ingestion in the turbo machinery, those sort of applications. Besides, oh, sorry, besides the granular applications, I would like to give you guys another example to highlight the customizability of this new model. With the new user-defined functions, user can now customize the agglomeration model for a wide range of non-granular applications as well. For example, let's look at how a user can customize this model to simulate towels within a spinning drum. So at the beginning of the simulation, user can use a table injector to specify the initial location and also the conditions of the particles, and then use the resin time of the particles as a criterion to bond the particles. And the layer of bonded particles is effectively a numerical towel. The bond stiffness is assigned to the towel along with the bond formation. So with the appropriate parameters, the user-defined bond stiffness can simulate fabric-like stretching and bending of the towels. And also with the new models, now user can explore a wider range of industrial application than before, whether it's granular or a non-granular. Like more details of this specific model can be found in more info path as well. Besides the new multi-phase molding capabilities, STAR is introducing new physics-based aging models for battery designs. The new model can help battery designer to predict battery cell degradation and improve battery life cycle. There are two main aging mechanisms STAR has introduced in this version. They are the solid electrolyte interface SEI film growth and the lithium plating film growth. Let's take a look at how this mechanism actually work. So let's look at a diagram on the right-hand side. We'll see that the SEI film is formed when the electron from the anode reacts with the electrolyte solvent and the lithium ion from the separator. On the other hand, the lithium plating occurs when the lithium ion fail to intercalate and reacts with the electrons at the anode surface. These aging mechanisms will eventually cause loss of capacity and increase in the internal resistance for batteries and degrading the battery over time. Importantly, these models are actually well validated with experimental results from a Modela Square project, which is a EU-funded research on advanced lithium storage system. An example of simulating film growth for a stack design battery is showcased right here. With the new models, battery designer can identify the concentrated areas where film growth is significant. In this case, will be the center of the stack, and well, actually, center of stack for both cases here, actually. And user can also like simulate multiple stacks simultaneously to observe like film growth across all the stacks as well. So now battery designer can benefit from these new physics-based aging models. More details on how to activate these models can be found using the more info path as well. Let's move on to the last feature in this category. Now surface-to-surface radiation model has now ported to the GPU solver. This allows computational intense heat transfer simulations to be computed using GPUs. The GPU native surface-to-surface radiation model is actually verified to produce a CPU equivalent solution to ensure accuracy. So if we look at the CPU solution and the GPU solution in the bottom right corner, they're essentially identical. But now with the GPU native capability, complex heat transfer simulation can benefit from the GPU-like performance, which offers the remarkable scalability. For example, if we look at the top right corner, that is a Corvette thermal management case. It is simulated in 3 different settings, 128 CPU cores, 4 A100 and, GPUs, and 8 A100 GPUs. Commonly, CPU solver would suffer from poor scalability at a high core counts. So in order to have the comparable performance against the A100 GPU solution to gain that speed up, more than 8 times the CPU cores would be needed, just due to the fact of the scalability and the limitation of CPU solver. But if we look at a GPU solver, it is showcasing a promising scalability where doubling the GPUs from 4 A100 to 8 A100 nearly double the speed up. We just finished the first category. Let's move on to the second one. Let's talk about solution acceleration. In this version, an isotropic mesh refinement in the boundary layer is now available for adaptive mesh refinement, also known as AMR. This new feature is targeting geometries with a strong curvature, like a leading edge of an airfoil or side mirrors of a car. And previously, the isotropic option was the only option for prism cell refinement. This option often over-refines the prism layer mesh, resulting in a lower computational efficiency. In this version, there are 3 new anisotropic options. They are normal, tangent, and criterion based. In the bottom right corner, you can see how different prism cell refinement affects the prism layer mesh. So if we look at the normal option, so the normal option would refine the prism layer mesh normal to the wall, but coarsen the mesh tangent to the wall. Vice versa, the tangent option will refine the prism layer mesh tangent to the wall, but coarsen the mesh normal to the wall. Let's take a look at the video in the top right corner. I would like to show you guys how you guys can activate these new options in 2406. Uh, Obviously, first, the adaptive mesh must be selected for the physics continua. And under the adaptive mesh node, user can find the prism cell refinement option within the properties window. And if we click on the drop-down list, we will see that uh, there are 3 new options besides the isotropic option. With these 3 new options, a significant amount of cells can be reduced and a noticeable of computation time can be saved. But we need to answer this one question first. How does the anisotropic mesh refinement affect the boundary layer? Whether the boundary layer is still being captured properly? So to answer this question, let's take a quick look on the check case to verify the anisotropic option is producing an equivalent result of the isotropic one. So as shown in the video, the check case is simulating a flow path and airfoil, and it is measuring the boundary layer profile at 2 different locations. Charts on the left-hand side are showcasing the velocity profiles measured at both of those locations. The isotropic option is highlighted in blue, and the anisotropic option normal is highlighted in red. We can see that the velocity profiles are identical between the isotropic option and the normal option, and at both locations as well. But without trading off any accuracy, the anisotropic option actually contains 4.8 times less cells compared to the isotropic option. So the benefit of using the anisotropic option is very promising. In this new version, a faster sliding mesh interface is introduced as well. This new sliding mesh interface mainly benefits the applications with unsteady flow that is driven by the rigid body motion like rotor blades, automotive wheels, mixing vessels, etc. These applications usually requires computational intense settings like high CPU core counts and a lot of computational time as needed. A faster sliding mesh interface can greatly reduce the cluster time with those sort of applications, and that can directly translate to cost savings. So in the previous version, there were 2 options for sliding mesh interface. They were the topology-based intersector in purple and the geometry-based intersector in red. Both of them are highlighted in the graph. And we can see that those 2 options has a quite poor scalability at high CPU core counts compared to the moving reference frame one, which is in light blue. The moving reference frame method is a cheaper alternative for modeling options, but also has its own downside as well. But if we look at the new metric-based intersector, is actually offering comparable scalability to the moving reference frame method, and is actually also requiring less memory usage compared to the other 2 options. And this less usage of memory can directly translate to the capability of loading a bigger mesh on the GPUs to take advantage of the GPU's performance as well. Besides the enhanced scalability, the new interface actually offers a faster interface calculations. So simulation with a large portion of interface mesh can gain a noticeable speed up. So applications like engine oil crank, where the majority of your mesh, well, at least a large portion of mesh is the cylinder wall, and that will be considered sliding mesh. And more info on how to activate this metric-based intersector can be found in the more info path down below as well. In this version, user can now finally manipulate turbulence model in stages. This new feature enables complex workflows to be native instead of relying on JavaScripting or like extensive macroing, especially for those complex workflows that involves high fidelity unsteady flow phenomena like vortex shedding or aeroacoustics to be native. One of the biggest challenge for those complex workflow is that they often require initialization with a solution converged from a different turbulence model, usually a lower fidelity turbulence model. This sort of turbulence model switch was not feasible in STAR previously, so user would have to implement scripting to bypass that constraint in the previous version. But those sort of scripts are hard to manage, maintain, and also hard to like troubleshoot sometimes. But now the turbulence model selection and deselections are available within stages, so user can ultimately couple stages with simulation operation to automate all these complex workflows that requires a switch in turbulence model. And this new approach with the stages is much more robust than JavaScript, which could easily break due to a version change or other sort of reasons. This new feature is especially useful for multi-stage turbulence model workflows like RANS to DES, InVisit to RANS, or even DES to LES, depends on your fidelity. So this is the last feature I'll go over today. But there are way more features are embedded in this new version and are worth exploring. I highly encourage you guys to go explore it. So I would like to share ways that you guys can explore the new features on your own, or even go more in depth on the features I covered today using the more info path I provided in the previous slide. More infos on the new features are usually found in the STAR-CCM Plus user guide or the release notes. You can access the user guide or release notes via the HTML link or the PDF files, obviously of your choice. Let me first walk you through how you guys can access the HTML link or the PDF file. So first you will need to visit the support center. That'll be your step one. And then under the product center, you will select the STAR-CCM Plus product. And then that will bring you to the product center for STAR-CCM Plus. And then under the product center, you'll see multiple tabs such as knowledge base, downloads, and documentation. So for this case, we'll select documentation tab. We click on that tab. It will bring you directly to the documentation page for the STAR-CCM Plus. Usually it brings you directly to the latest version. If not, you can change in the top right corner within that page. And then step 6 would be you can type in the keyword in the search bar. So for here, I'm just using user guide as an example. If you type in user guide and hit filter, it will filter all the documentation related to STAR-CCM, the latest version of STAR-CCM Plus, and then filter it by a user guide. And then usually it'll be really easy to spot the user guide by itself for the STAR-CCM Plus. They usually come in the HTML link and the huge PDF format. And you can select either one and start accessing the document. So if you're interested in looking into the release note, you can repeat step 6 and 7 by simply replacing the keyword from user guide to release note. There's two ways to access the information for the new features. Right now, I'll start with the HTML users. So if you're HTML users, you can access the document simply by clicking the HTML link. That will bring you to the home page for STAR-CCM Plus user guide. I highly recommend bookmarking this page. This page is really handy when it comes down to troubleshooting or debugging your model. And within the home page, you will see there's a lot of like boxes. So right here, if we're interested in the new features, we'll spot the box name new features and enhancement in the Simcenter STAR-CCM Plus 2406. Clicking on that specific box would bring you to the overview page for the new features in 2406. In the center of this slide, you'll see that there's the top new features, having a really short description in the middle. That's basically just STAR highlighting their top features for this version, and the rest of the features are all categorized into different tabs. You can see the tabs are on the left-hand side, and also on the bottom of the screen. You can pick any of these tabs to start exploring. So for example, if we're interested to see what is new in the meshing category, then we'll simply click on the mesh tab, and then you'll be brought to the summary of all the new features related to meshing. For example, like what's new in surface repair, surface mesh, and volume mesh, etc. So now I would like to also show you guys how to use the more info path I mentioned in all the previous slides. This will help guide you guys directly to the information and save time from searching around. Right here, I'm using the more info path from the SPH slide as an example. For HTML user, the process is very simple. You guys can extract the last item of this path and search it in the user guide's search bar. And you'll see among the search results, you just have to select the matching one that matches the last part of the more info path, and then click on it. It'll bring you to the new modified tutorial for SPH inlet boundary conditions, and then you can start exploring how to set up the new inlet boundary conditions from the SPH module and start exploring and learning. However, it's a little bit different if you're a PDF users, but it's also quite simple regardless. You would open the PDF file in either a browser or PDF reader. In this example, I'm using a PDF reader. The process is very similar between the browser and the PDF reader. So you would click on the bookmark tab or a bookmark tab equivalent in the browser and expand that tab. Then you'll see a lot of subtabs under this bookmark tab. And these subtabs are basically the boxes you saw in the HTML version of the homepage. And then similarly, we want to find that subtab that is named the new features and enhancement in Simcenter STAR-CCM plus 2406. If we click on the subtab, it will bring you to a similar page for the overview of the new features. Everything is identical description-wise. The only thing is the layout is a bit different between the PDF version and the HTML version. The more different part is actually the usage, the utilization of the more info path. So for a PDF user, you need to navigate through the bookmark tab, like going through folders or directories in the File Explorer. You would basically ignore the first part of the more info path, which says the home, because basically when you click on open the bookmark tab, that is basically going to the home page. And then you just click through each part of that more info path after the home part. Then, for example, using the SPH as well, is you click on tutorials, then you expand the tutorial tabs, you click on the multi-phase flow tab, you expand that, and then you can find the smooth particle hydrodynamic gearbox lubrication tutorial right there. And you click on it, it'll bring you to the similar page you saw before for the tutorials, but just in different layouts. Since we talked about the modified tutorials for the SPH module, I also would like to share how you guys can obtain the tutorial files that is related to all those modules or the new updated tutorials. First, you go to the product center again, but this time you won't be selecting the documentation. You'll click on the downloads, and then you'll be brought to the downloads page. And then usually it's already at the latest version, and then you can just directly click the big box on the bottom left, and that will take you to the downloads page for all the related downloads for the latest version 2406. But to make it even more simpler, we can click on the tag on the left-hand side called related files and documentation. That would help filter all the downloads down to that specific tag. When you did that, then all the search result will be very simple, and you can see the STAR-CCM Plus tutorial files right there in 2 different OS, and they're all in 7-zip format. Well, thank you guys for listening to today's webinar. I'm more than happy to answer any questions. Let me look at the chat, or if you guys have any questions, you guys can ask in the chat or the Q&A section. Either way would be perfect. So there is a question that was asked about how do you determine what sort of like particle diameter for the resolve transition model for the MMP to LMP phase interaction. So to answer that, it really depends on what kind of length scale you want to solve, because it really comes down to because you have to refine all the free services if you're willing to resolve it. So it would basically determine your length scale. That's one of the questions that was asked. I see there's also another questions on the parallel bond model. So that model is specifically it is somewhat removed, but it is basically merged into the particle agglomeration model. So they're basically the same thing, but the particle agglomeration is adding a lot more capability on top of that specific model. Is there any more questions? If not, well, thank you guys for coming. I wish you guys have a good day.